Hi everyone. A few comments about systems of linear equations in three unknowns, x, y, and z, let's say. In section 8.1, we'll solve this kind of a system using matrices, boxes of numbers. And these equations are going to be graphed in three space, not as lines, but as planes. Imagine a piece of paper extending infinitely far. Now, these three equations we can graph in GeoGebra.org. Look under New Math Apps, 3D Calculator. The x-axis here is in red, the y-axis is in green, and the z-axis is in blue. The way it's oriented now, it's like if you look in this direction, you're looking down on the xy plane if you look like so. But on a whiteboard, typically we would orient things so that the positive x-axis is actually kind of pointing at you. And then the y-axis and the z-axis, the yz plane, would be the whiteboard. So we tend to draw it like this, where the positive x-axis is pointing at you. Here, I use that orientation, and I typed in the three equations from the system here. The graph of this first equation is a plane. There's even a little note here, equation 1. By the way, to change the color, you can go to Settings, Color, you can change the color, you can change the style, put in lines, grid lines. All right. The second equation gives us a plane in red. And notice that the blue plane and the red plane intersect in a line. Equation 3, that's going to intersect that line at a point, and the point is the common point of intersection. -6, 8, 2. It turns out that's the solution for the system. We'll find that in 8.1. I'll rotate this around, and you can see how this point lies on all three planes. And in order to have a solution to this system, we need a point, a solution point, to lie on all three graphs. The point has to lie on all three graphs. It's not enough just to lie on two of them. For example, here, the blue plane and the purple plane intersect in a line with infinitely many points, but the only solution is this point, this blue point, where we're also intersecting with the red plane. This blue point is where all three planes meet. It's the sole solution in the solution set. For these linear systems, we can only get no solutions. Imagine parallel planes, like in a science fiction story. No common points of intersection. You could have one intersection point, like we did in this example here, or infinitely many solutions. For example, maybe we have the same stupid plane. 1, 2, and 3, same stupid plane. Or for that matter, we could have a plane on top of itself, and there's a third plane coming in that gives us a whole line of solutions. We'd have infinitely many solutions, but on a line. Okay, now I'd like to go back to the original setup. Let's reorient these. Okay, so together, the x-axis in red and the y-axis in green make the xy plane. That has equation z equals 0. Kind of hard to see here. So it's kind of hard to see, but in blue, okay, that's like the floor. That's the xy plane, z equals 0. It contains the x and y axes. Whoops. Now, x equals 0 is the yz plane. I'll put that in red. X equals 0 is the yz plane. That's like the whiteboard. It contains the y-axis and the z-axis. Y equals 0 gives us the y equals 0 gives us the xz plane. It's like a wall on the side. Put that in purple. All right. So y equals 0 is the xz plane, which contains the x-axis in red, and the z-axis in blue. And what is their common point of intersection? What's the solution to this system? X equals 0, y equals 0, z equals 0 is going to be the origin. That's the point where all three planes meet. And these three coordinate planes, z equals 0, the floor, x equals 0, the whiteboard, y equals 0, this purple wall here. These three coordinate planes will divide 3 space into 8 octants. Here's octant 1, where everything's positive. Okay, we have 4 octant. Whoops. All right, hold on. There, we have 4 octants above the blue xy plane, z equals 0, and we have 4 octants below the xy plane. The 3 coordinate planes divide up 3 space into 8 octants. Let that sink in. All right.